Hi, welcome to this video on Chapter 11, which is gases. And in this video, we're going to be talking about ideal gases specifically. So there's really kind of a difference with ideal versus real. A real gas is the gases that we would deal with in the real world, right? So if we blow up a balloon with helium or something, how are those gas particles behaving? And if I take that balloon and I drive up Pikes Peak in Colorado and I end up at a high elevation, what happens to those gas particles? So those would be what's happening in real experimental time. Ideal gases are exactly what they sound like. Anything that's ideal is an ideal condition, or it's something that's easier to look at or study, right? It's what we would prefer to happen. So ideal gases are not the same as a real gas. But when scientists study gases, it's hard to study them with lots of different external conditions. So typically, we study what are called ideal gases. So ideal gases are gases that exist in ideal conditions. So this comes back to our concepts of intermolecular forces. We know that there's attractive forces between molecules no matter what. Now, some are stronger than others, right? So gas molecules typically have broken all of their intermolecular forces and have no attractions to each other. But really, we know that there's London dispersion forces and nonpolar and then dipole-dipole and hydrogen bonding. Those attractive forces still exist, which are going to tend to pull gases closer together or make them act less like a gas. So what we tend to do when we study gases is we try to put them in ideal conditions. So ideal conditions for a gas would minimize, the key here is, for an ideal condition is it's going to minimize attractive forces. And so that's all we're trying to do, is we're trying to minimize those IMFs so that they don't attract to each other and stick together, right? Because then they would be going to a liquid phase instead. So what would we want? Well, pressure, right, is the pressure the gas molecules are exerting. And so we want to make sure that those are going to be very low pressures. We do not want to push or try to compact our gases together. We want to give them plenty of space or volume so that they can have low pressures typically. And then temperatures. We want to keep the temperature of our gas molecules really high. We want them to have a lot of kinetic energy, so therefore they don't have attractive forces. So we want to have very high temperatures. So those would be the ideal conditions that we would want to study gases in. We don't want to study a gas at really high pressure because that's going to force the gas molecules to be together. And that's going to typically force them into a liquid or a solid state. And the same with temperatures. If I study them at really cold temperatures, the gas molecules aren't going to be moving as much, which is going to be more likely to form intermolecular forces. So ideal gases obey the kinetic molecular theory at all times, which is why we prefer them, right? So the kinetic molecular theory we previously learned about is that they don't take up any space or volume. So we pretend that our gas molecules occupy the volume of the container and that there's really the volume of the container, and that we don't take the individual molecules' volumes into consideration. We also assume they have no intermolecular force attractions or repulsions, which is why we set those conditions. And they would obey these conditions under all, no matter what, right? But in the real world, no gas is truly ideal. So we're going to study ideal gases and talk about how we use the ideal gas concept to get us some good information. But then we're also going to spend some time talking about real gases, which is what the behaviors we would see and study more in lab. But really, real world, real gases exist. But in the lab settings, for us to be able to do and find information and do experiments, a lot of times we want those ideal conditions. So under ideal conditions, there is an ideal gas law that has been found. a law, just to remind you, is an observation of nature. And so in ideal conditions, scientists found these observations of gases at those ideal conditions. And so they found these observations of gases that always exist, and no matter what, they're observations of nature. And so the ideal gas law is actually a mathematical law that was developed, but what it does is it describes, oops, I picked the wrong thing. It describes the gas behavior with all variables: pressure, volume, temperature. So basically it's looking at one gas at a set of conditions. And it allows us to study that one gas under those conditions. We can use this most often to find the amount of gas that we have, like let's say in a balloon or something like that. So we could find those moles of gas. We can also use it to find the pressure. So we can find any of our variables with our sets of conditions. The mathematical equation that relates or explains this law that scientists came up with is PV equals nRT, which is called the Pivnert equation a lot of times. And so I don't know why when I was a kid, I always thought of it as like the pervert equation. I don't know why. Like, I have no clue why. But hopefully it makes you laugh and it helps you remember it. The PV equals nRT equation is Pivnert to us science teachers. And it basically relates all of the variables for one gas under one set of conditions. And it's all related to this ideal gas constant. So a constant is something that we just never change, and it makes the mathematical equation work under all sets of variables. So the ideal gas constant is the R. So that's this R portion. So that's the only thing that we would not have conditions for. We just know. This R value, I'm going to list in your notes, is also on your formula chart. The R value is dependent on the pressure unit. Okay, so there's different R values. So if you're using ATMs as your pressure unit, then your ideal gas constant is 0.0821. And then this is where it's funny. The units of the R are liters times ATMs over moles times Kelvin. So that is a unit, just like meters per second, whatever. But notice that we use the ATM pressure unit for this R value. For the R value, if it is in a millimeters of mercury, which we also see, is going to be 62.4 liters times millimeters of mercury. I didn't really leave myself a lot of room here. Over moles times Kelvin. So again, same thing, liters, moles, Kelvin, but we changed the pressure unit. So we changed the R value. There's also a kPa one, which is the Pascal. Pascal is the SI unit, and that is 8.314 liters times kPas over moles times Kelvin. So whichever pressure unit we're using determines which number we plug in for the R constant. The rest of the variables we would be provided because those would be the set of conditions for our gas, and when we would be looking for one. So really it's some simple algebra is what we're doing here, because mathematically all these variables come together. If the pressure that's exerted by a gas at 25 degrees Celsius in a volume of 0.044 liters is 3.81 ATMs, how many moles of gas are present? So labeling our variables. Now you can label them individually or you can label them in your problem, however you want to do it. So first thing is pressure. So pressure units are ATMs, millimeters of mercury, or torr, or kPa. So this pressure unit is 3.81 ATMs. My volume is going to be in milliliters or liters. In the volume of this scenario, it must be in liters. That's because if we come back over here and look at the R values, the R constant units are always liters. So your volume must be liters here. There's no option, okay? So you have to have the volume in liters. It's already in liters for us, 0.044 liters. The R value I want to use is going to be 0.0821, right? Because that's the liter times ATMs over moles times Kelvin. So notice this ATM unit has to match with the pressure unit that we have. And then my temperature must be in Kelvin. Again, same scenario. We cannot use the Celsius thing. That's because our R value uses the K or the Kelvin. So we have to make sure those units are going to cancel. So our temperature is going to be 25.0 degrees Celsius plus 273. When we add those, we keep that decimal for sig figs. So 25.0 plus 273 becomes 298. It's actually going to be 298.0 degrees Celsius, because technically the 273 is not a measured value, right? It's just a conversion. So the measured value keeps that one decimal place. And then we're looking for moles in this case. So that's the N. That's what we don't have. So really all we're doing is plugging in and solving. I prefer to solve my equation before I plug in, but you can plug your numbers in and then solve either way. But I'm going to show you how I would do it with plugging in my information, what I want. So I have PV equals nRT. And so I am going to solve, and the main reason I do this is because in physics, you're going to have to learn to solve the variables. So I want to keep in, so I'm going to divide by RT on both sides. So we just do the opposite, right? And so that moves that over. So my moles are going to equal my pressure, so 3.81 ATMs times, notice I'm putting units on all my numbers, so it's nice and neat and organized and easy to see. My V is going to be 0.044 liters over my R, and I'm going to put my unit on my R, so 0.0821. Now the reason I'm going to put my unit here, liters times ATMs over moles times Kelvin, is because then I can check to make sure all my units cancel or in the right unit, and that I converted them if I was supposed to. And then my temperature is going to be 298.0 degrees, not degrees Celsius, Kelvin. So then when I go back and I check my units, right? ATMs cancels with the pressure, the liters cancel, and then my Kelvin cancels. If the units don't all cancel, leaving behind the single unit you want, then you have something wrong, so you need to fix it. So that's why putting your R value unit is there. It's kind of a pain to write, but it's going to help you in the long run not make mistakes. So I'm going to take 3.81, and I'm going to multiply that by 0.044, divide it by 0.0821, and then I divide again by 298. So sig figs, I want the fewest number because I'm multiplying them all together, right? So I look at each one. I've got 3 sig figs, I've got 2 sig figs, and here I've got 4. So I'm going to go with 2, my fewest number of sig figs. So I get 0.00, and then I need 2 sig figs. So it's 685, so it's going to be 69 moles of the gas. And so in this case, that's how many moles of gas would be there. Now we could also convert this to grams if we wanted, right? Because once we have moles of something, we could find grams if we know what kind of gas it is. All right, so let's do one more quick example. So this is how I would normally work the problem, but I kind of broke it down for you a little bit. I normally would mark what I have in my problem. So it says determine the temperature. So temperature is what I want, right? And I have 2.49 grams of oxygen. Remember that oxygen is diatomic, so that's O2. And so keep in mind though, grams is not the same thing as moles. So I'm gonna need to convert my grams to moles if I wanna be able to plug into any of my formulas, okay? And then I've got 1 liter, that's gonna be my volume. And my pressure is 143 kPAs. So I have this set of conditions, and moles are in, right? So don't forget that. I have my set of conditions. So what I want to do here is I want to first get moles so then I can plug in, right? Because PV equals nRT. Well, I'm trying to solve for T, so I'm going to divide by nR, right? Oops, I did that a little weird, but so that's essentially what I want. So I have pressure, I have volume, I have the R because that's a constant. I need moles. So first thing I'm going to do is 2.49 grams of oxygen O2. That's important that you pay attention to that because that means that there's 32 grams of oxygen for every 1 mole of oxygen, not 16. So that doubles your molar mass. So 2.49 divided by 32 gives me with 3 sig figs, 0.778 moles. All right. So then once I have my moles with correct sig figs, right, then I can plug in. Temperature is going to equal, and remember that temperature is going to come out. It doesn't specify it has to be in Celsius, so I can leave it in Kelvin. So I'm going to plug in what I have. I have 143 kPAs times my volume, which is 1.00 liters, over my N, which we just found, 0.0778 moles, and then the R value. The R value I want to use here needs to be, so going back up here and looking, the one that has kPa in it. So we're going to use this one, right? So we need to make sure it matches up. So we're going to use 8.314, and it's going to be liters times kPAs over moles times Kelvin. All right, checking our units to make sure everything cancels really quick. We've got kPa cancels, so we know we have the right R value. Liters canceling, and we got moles canceling. So that's going to leave our temperature as Kelvin. So our temperature is going to be 143 times 1, which is itself, divided by 0.0778, and then divide again by 8.314. All right, so when I do that, I get 200, and for sig figs, I have, if I go back, I've got 3, so I'm going to go with 3. So 221 Kelvin is my answer.